Okay, so again, based upon the comparison of the relative stability, we can introduce the two terms. And the two terms basically is a measurement of the relative stability. And the two terms basically defined by this. Again, we making a Nyquist plot of a certain open loop systems. Okay, so basically this is the open loop system. Okay, and then the curve will be something like this. Okay, and let me label the 1, -1, 0 is here. Under these situations, we can define the phase margin and gain margin for a stable system. Basically, this is a stable system. Okay, so let me say the GH is a stable. Okay. So under these situations, basically here we take the origin as a center, and we take the radius of 1 to draw a circle, and that circle will help us to define the two terms. So let me do it. So this is a circle of a radius equal to 1. Okay. So for this case, then we can define the first one. Let me define the phase margin. The phase margin is this. Basically, we find the intersections of this circle to the plot, which means at this point. Then we're connecting that point to the origin to calculate the angle. Basically, this is the angle of the GH. Let me define this is the omega CG. Okay, and I'm going to explain what this means. But here we just label. Here you can see again in this drawing, omega approaching to here is omega approaching to infinity, and for this one, the omega is approaching to 0. So basically here we have so many sampling points. In this particular point, I simply define it as omega CG. Okay. So this angle basically defined is the angle of the GH at J omega CG, right? Okay. And the phase margin basically is defined by this. This is called the phase margin. Okay, sometimes the people using PM. Okay, and from here you can simply graphically, basically that is the angle measured from. You find the intersections with the radius 1, and you make a plot, and that is this angle here. Okay, and the phase margin basically defined by this. And in terms of the mathematical the formulation, basically that is equal to this is negative, and this from here to here is 180. So basically here you can write it up is 180 degrees, and plus GH at J omega CG. Okay. So how to find the omega CG? Later we can use one example to demonstrate this. But anyhow, graphically, that is the phase margin here. And here the omega CG is defined as we call the gain crossover frequency. Okay, so that means this C means crossover, G means gain. So basically that meaning the gain equal to 1. So that means this magnitude, we take the radius equal to 1, representing that the magnitude equal to 1. Okay, that's the definition here. So that is for the phase margin. Then the second one, we're going to define the gain margin. The gain margin is defined by this. Again, we take the second sampling omega here. So basically this is the point on the Nyquist plot, and let me call this is called the omega CP. Okay. So at this particular frequencies, we will be able to know the magnitude. So basically here, we're linking from here to here. This gives us the magnitude of the GH, the magnitude of the open loop systems, and which is taken at omega CP. Okay? Graphically, it's very, very simple. You simply take your ruler to measure the distance here. That's it. Mathematically, we have to do these calculations. Okay? So the gain margin, and usually we are using the notations, is using kg. This is the symbols using in our textbook. Kg simply is defined by 1 over these numbers. Okay. Again, to pick up the phase margin and gain margin, I think the easiest way is to work on the graph. Okay. Because on the graph, everything is very, very straightforward. For the phase margin, you simply measure this angle here. For the gain margin, you measure this distance, and then 1 divided by this distance, that gives you the gain margin. For example, if you measure this distance is 0.5, then gain margin equal to 2. If this distance is 0.1, then gain margin equal to 10. Okay? Okay. And under these situations, this one is called the phase. This one is called the phase crossover frequencies. I know sometimes this one, the definition of this is kind of bothersome. Even for myself, I need to look up, but you know what we mean. Okay, that is just for the communications here. Good? Okay, so with the introductions of the phase margin, gain margin, we look at our original example here. And we try to apply. So for a stable, for a more stable systems, from here you can see for these systems, let me plot the circle here. So this is the circle of radius equal to 1. Okay, so basically from here you can see for a more stable systems, for example this one, this is our gain crossover frequencies, and corresponding to this, we link the point here. This one has a larger phase angle than the green one. For the green color that is less stable, it has, for example, this phase margin seems to be, say, 30 degrees. And for this more stable system, is phase margin seems, for this case, for this drawing, seems to be 60 degrees. Be good? And also we can compare for this one, again, this is corresponding phase crossover frequencies. And so from here, this measurement seems is equal to about 1/3. So the gain margin corresponding to this system is 1 divided by 1/3, about 3, corresponding to the less stable system that corresponding to here, you measure it, this is about 0.6. So gain margin corresponding to this is 1 divided by 0.6, about 1.3, right? So compared to this one, for a more stable systems, it has a larger phase margin and it has larger gain margins. A less stable system, it has less. Be good? Okay. And one more thing before we jump into the examples is I want to show you how to map the gain margin, phase margin onto the body plots. So we consider the plot of GH okay, stable GH. Okay, so here is the magnitude GH, and in dB, let me get prepared. And this is the phase angle in degrees, and this is the log omega. Okay. So from here, we want to right now for these demonstrations, we focus on the stable systems. So here, let me kind of schematically draw the plots here. So for example, this plot is something like this. Okay. And then we convert to our definitions here. For this plot, how to define the phase margin. Phase margin is phase margin is the angle of the plot at these frequencies, right? And what is that frequency? This frequency happened is when magnitude equal to 1. So let me define this. This is a 0 dB here. This is a 0 dB. And basically that means this corresponding to our situation, this 0 dB, that is the label is GH, magnitude equal to 1, right? And here. So this, by our definitions, when the magnitude of the GH equal to 1, that is the intersection with the radius 1. That is the frequency we define as omega CG. You good? So this is our omega CG. Okay? And at omega CG, for a stable system, the phase angle, the phase margin must be positive, or its phase angle should be less than 180 degrees, minus 180 degrees. So for this case, let me label it carefully. Let me just move it a little bit slower here. Okay, so this is minus 180 and minus 90 and 0 degrees. Okay, log omega. So at the omega CG, the phase angle should be something like this. You can see right now for this case, at omega CG, the phase of this one is about, say, for this demonstration, about, say, minus 120. So by this definition, you can see what is a phase name. The PM, the phase margin, basically is how much we still away from minus 80. So since this is our threshold, so this is our phase margin. You good? So now we try to get used to, and sometimes this one, again, the best way to pick up the two definition is by observing on the graph. And two ways, either you can do it on the Nyquist plot, and here showing is on the body plot here. Okay. So now let me define the gain margin. Gain margin happens is to measure the magnitude when at this point. At that point, corresponding is the angle is minus 180 degrees. So here, the cross section here, that is defined as the crossover of the phase. Okay, so phase crossover frequency. So that this frequency is defined as a WCP. We're good? Okay, so under that situation, we can make that one here. So now you can see the gain margin basically is defined by this one. Okay, so what is this? Kg, let me do a little bit more calculation. Kg equal to 1 divided by omega GH, and that is at J omega Cp. Okay, so basically this is the magnitude, and right now on the body plot we convert the magnitude in decibel. So that means 20 times log kg, I simply convert it into decibel, okay? So basically I multiply the magnitude with 20 and then log, and basically that is 20 times this one. Let me do this one quickly. So basically this is 20 and minus 20 times log, 20 log. Right? Is that right? Okay, good. And so in terms of if we convert it into the unit of the decibel, then the gain margin should be in these expressions. And these numbers, in terms of our graphics, that number for stable system must be less than 1. Okay, so the magnitude of the gain at that should be less than 1. So that means this log should be negative in nature. So negative, put negative together, basically become a positive. And actually the whole numbers here is represented graphically by this. 0, basically this is equal to 0 minus that 1. So basically that is simply is this one here. If you want to look at this graphically, this is our gain margins. Gain margins simply indicate in terms of the decibel how below the magnitude from the 0 dB. The lower that the system there, then the system is more stable. Be good? So right now, basically here we indicate this is the phase margin, this is the gain margin for a stable system. Okay. And you might refer to, say, what happened to unstable systems. For unstable systems, then its plot will be something like this. This is minus 1, 0, and the plot will be encircle this one. For this case, you can try to, using the definitions, so basically this is our circle here. Okay, so we can try again. Let me define the phase margin. So basically here, this is the crossover, the gain crossover frequencies. So by doing this one, you can see this is the magnitude of the systems. So right now, the gain margin basically defined by this, which become negative. Okay, so that means you can refer to our textbook for unstable system. So here, let me skip over the unstable system because that is less used. So we stick with this one, and we can look at one example here. Yes, question.
So you kind of talked about this before, so I'm sorry, but why is -1, 0 this critical?
Yes. The question, we can stop at this moment.